This is the report from Group 1. Is information more fundamental than matter and energy? And I have to start by saying that I work at New Scientist magazine. I'm not a physicist. So my colleagues in Group 1 will step in and interject if they need to. But they felt that I was objective and I would be able to comment on this. What I find when you have a group of 12 physicists and philosophers together, then you usually get 12 different answers. However, on this question, is information more fundamental than matter and energy, we reached a consensus surprisingly quickly. That answer was no. But instead of then diving off into the sea, we then came up with a series of caveats. And then this is where the physics and philosophy really shone. So our answer was no, but. And we felt that this was actually the wrong question to be asking. And we started asking, well, what question should we be asking instead? And instead we thought, well, how is information more fundamental than matter or energy? Is there a better descriptor of the world? Is that really what we mean by the word fundamental? You know, we were actually disagreeing over the words fundamental. This whole what is fundamental? But of course, the elephant in the room was the big question, what the hell is information anyway? What we did agree on, almost, is that something is more fundamental than matter and energy. We had one person sitting on the wall over that question, and we also had an abstainer as well. But we took a vote, and we agreed that something is more important. The question is what? And this is where the consensus dissipated somewhat. Some of us felt it was the laws of physics. Others, that it was quantum field theory, software, the Hamiltonian. It could be geometry and space-time, or it could be mathematics, which then led us to the conclusion that perhaps what's more fundamental than matter and energy is, in fact, Max Tegmark. So I probably won't be able to answer any of your questions, and I may have to pass over to my colleagues. But thank you.
What is Max Tegmark?
Can you define Max?
I can remember that. Can you just flip the list out because I can't remember all the others. I can remember Max Tegmark.
Well, let's have a round of applause for Group 1 here. Next up is group number 2. Will information physics be necessary to understand quantum gravity?
So I rather quickly decided that explaining quantum gravity without using information concepts, whether it's qubits or holography or things like that, would be like explaining it without using the letter E. I mean, obviously it's possible in principle, and obviously you wouldn't want to do it. So then I went swimming. So I think I'm going to defer to the people who actually discuss this in more depth.
All right, so who comes up here?
You.
Welcome. A round of applause.
Okay, well, a bit more of a report from the committee. It was actually divided, since it was such a large group, into two camps, either those who thought that quantum information is important for quantum gravity, or those who don't think that that's the case. And so there was discussion in each of the camps, and then we came together. And actually, I think, though, largely Scott got the right answer. He knew the answer, he just went swimming. Namely that, I think we came together and realized that, maybe quantum information concepts are not absolutely essential for describing quantum gravity, but certainly if quantum gravity is something that fits within the framework of quantum mechanics, then just as with any other quantum mechanical setup or system, quantum information concepts can be very useful. And so there was that distinction made, maybe not absolutely necessary, but useful. And actually, I would go one step further, and I would say that quite possibly if we're going to figure out quantum gravity, quantum information concepts may be a very important guide, because we need to understand transfer of quantum information and how we modify, say, quantum field theory. And we need some additional structure, and I think quantum information may well provide us some of the guidance. So in practice, maybe it is necessary. That's just injecting my own personal opinion on that. So I can also state that there was various discussion about aspects of the black hole information paradox, because that's where we really encounter most directly the connection between quantum information and quantum gravity. So I guess that's it.
Great, thank you so much. Quick question here.
Not so much a question as a comment. I think the question that maybe...
Wait, come up and talk in the mic.
Are we on item 3 now, or is that 2?
I think this is 2. Yeah. So I think the operationally relevant question is, will information, or quantum information theory, be a useful thing to think about in order to understand quantum gravity? And I think to that the answer is definitely yes. Whether or not in the end it's the most fundamental concept, but we've just seen this again in the context of the firewall paradox. I mean, these were tools from quantum information theory that were applied to this problem, and at the very least I think we can say that they're causing us to rethink the boundaries of the validity of classical gravity and semi-classical physics.
Great. Let's hold off on the questions a little bit, since we want to give everybody a chance here before Designers talk at 5. We also have an entire session dedicated to arguing about firewalls and quantum gravity later in the week, so hold on to your fire and your firewall. And next up, well, a round of applause for group 2 again. What sorts of information do physical, chemical, biological, and mental processes process, and how? Raise your hand if you were in group 3. I see zilch. Okay, who was in group 4? Raise your hand. Lots of hands. Who is the official ambassador? Jeremy? Welcome, Jeremy. He's going to tell us about what can information tell us about foundational questions in quantum mechanics.
Thank you, Max. Well, I hope you won't mind, Max, if I say that Group 4 was lucky to have something co-fundamental, as we philosophers say, with Max Tegmark, called Bill Wooters, who began by saying that the spread of information theoretic axiomatization of quantum physics was, noteworthy and worth examining, though he hadn't himself taken part in it, and that he held out the long-term hope that we would perhaps understand the quantum state, not in the manner of a traditional hidden variable theory as something like a classical statistical mechanical state of ignorance, of partial ignorance, but as in some looser way an epistemic state. And those two themes dominated the discussion. Not that we went down the axiomatizations in terms of information theory in detail, but we had an extended discussion of Carlo Rovelli's position through the good fortune to have Carlo Rovelli in the group. So I hope Carlo will forgive me if I summarize his position as saying that it is a cousin of the Everettian relative state endowed with insights about relative information between states of systems. So there was an extended discussion of that, but that led to general questions about subjective versus objective, intrinsic versus extrinsic, and relative to a parameter versus fixed without a parameter needing to be set. And we soon concluded that these were three independent distinctions. And there was some discussion of classical statistical mechanics in that regard, where the choice of variables to look at, or indeed the choice of the choice of a coarse graining scheme, may be means dependent, as Wayne Myhrvold put it, or interest relative, but it's not necessarily subjective, because, and so on. And then in conclusion, you'll be glad to know that after these generalities, there were some more specific. We came down to the ground on quantum teleportation on the one hand and weak measurement on the other. And in this connection, Wayne Myhrvold emphasized that what gets communicated from one wing to the other is 2 classical bits, or as emerged in discussion, more precisely said, what gets transmitted is first of all the E bit of the shared singlet, followed by the 2 classical bits, which has the effect that a Q bit, namely the unknown state, is transmitted. But after this discussion, lucidly led by Wayne, I did feel that the mystification of teleportation had evaporated. So if it's still mysterious to you, ask a member of Group 4. And if weak measurement is still mysterious to you, ask Jeff Tolleson, who explained how one can have in a limit of a large ensemble a limitingly zero disturbance of each individual system while having a positive given rate of information acquisition. So that, I think, is Group 4. Thank you.
So Max just realized he was the theory of everything and left. So I've taken over. So next is Group 5, the connections between information and probability. Who was in Group 5?
Actually, we spent most of our time discussing 3 main questions, and the first 2 were more or less connected to what we heard in the morning sessions rather than the assigned topic of our group. So the first really came out of Fred Adams's presentation on complexity and Shannon information, and the question whether the first topic should be a function of the second one. We discussed this a little bit and tried to see what he meant, and I think the issue that came out of this discussion, that at least I found enlightening, is the kind of complexity he was talking about, something that may be displayed by a pattern in a diagram, is actually a structured pattern. It has this fractal type of patterns, and things like that really depend on the choice of a geometry or a metric in that space. Now, on the other hand, the Shannon information is completely insensitive to that choice, and so as a simple example, you could think of a pattern in some particular variable. You could perform a Fourier transform or any other invertible one-to-one transformation, and that would be completely would preserve all the information, but it would change the pattern around into something you could hardly recognize anymore. So if you take some spatial image and perform a spatial Fourier transform, all you would see in the transform is just indistinguishable from random noise. But the same information is still there, so if you perform the inverse transformation, you would get the same figure back again. So although these transformations preserve information, they don't preserve the complex pattern you could see. And in that sense, we think that complexity, in the sense of a complex structured pattern, is not simply a function of the information. The second issue we talked about a lot was actually more Kevin Knott's work on how, I'm not quite sure how to summarize that, but Kevin showed us how in this particular axiomatic approach that he has developed together, I believe, with Philip Goyal, how merely assuming a ordering structure with an associative rule of combination can lead to axioms or properties of probability theory. And in this approach, you can use both classical or quantum theory. And so you would get additivity either for probabilities or for probability amplitudes in the Feynman approach to quantum theory. And that was a very enlightening clarification of what was very briefly discussed in one of his slides. It led us also to some discussion about what would have to change if you were to go over to Quartonian types of quantum mechanics, in which you don't use a complex Hilbert space, but a more complex Hilbert space without using complex numbers. And we believe that Bill Wooders had done some work on that, but we didn't actually have the details with us. So maybe Bill would try to enlighten us on that issue again. The third topic we discussed was perhaps more to the point of what we were assigned. This was actually Susan's question. She said she was really frustrated about the Shannon information measure and wondered how you could actually use it in the concrete examples like machine learning, if you want to build a robot, where, for example, you would have a robot with a little sensor, and every step, depending on the information that sensor gives to the machine, you would either perform a step to the left or to the right, or decide to make one step forward. And you can put a machine like a little robot like that into an environment and try to see how it can learn about its environment and acquire new information. Now, if you work on a problem like that and you want to use the Shannon information, then the first obstacle you meet with is that in order to even define Shannon's information, you have to have probability distribution. But that machine doesn't have a probability distribution. Of course, you could try to program it to have some particular Bayesian prior or things like that. But that would mean that you would have to build in all kinds of assumptions into how the machine is going to learn from its environment, which you might not be willing to do because you want to make it to be able to learn in any kind of environment. And so the question was really, is there some useful kind of information that would work if you only have, single events or something that would avoid having to use a probability distribution? And actually, I think that we didn't find any useful idea about how you could approach that problem. And so it seems like the Shannon information measure is not always useful to, or at least doesn't help us to solve real-life problems like that. And I see there is a question from...
Maybe one question?
Yeah, sure.
Isn't somehow all modern philosophy of science telling us that the way you're phrasing the problem is ill-posed? I mean, isn't any learning based on previous knowledge of some sort? So why don't you just... What is... I mean, it seems to me this mythology of no prior probability is a mythology we've abandoned quite some time ago. Is a mythology that is some idealization that we have abandoned quite some time ago. So what's wrong with prior probabilities? We can change probability, we update priors, we change assumptions, but we start with assumptions any learning.
Well, I'm not saying there's anything wrong with it. I'm just reporting that it seems to mean that there is no assumption-free approach that you can take with respect to learning. And I'm not saying that that's wrong, but it seems to be frustrating, at least from some point of view.
Okay, thank you.
Okay, since we didn't raise our hands, let me begin by acknowledging my group. Our group was big and loud and interesting. We had me, Lawrence Doyle, Farzad Weiser, Alan Guth, Bill Portier, Michael Vassar, Ben Schleyer, and then Jan Tallen joined us. So we were supposed to talk about whether or not information is preserved or not, and we kind of sort of talked about that. But we first spent the first hour talking about the distinction between information of different kinds, thermodynamic entropy and complexity, and we reiterated the importance to keep those separate. And then it was pointed out that if you look at the microscopic scale, where you look at quantum information, we have the result, like one of the speakers talked about this morning, that quantum information is preserved. So the question is simply yes if you look at an isolated quantum system on a small enough scale. But if you look at things on a larger scale, you get a different answer. So one of the things that we stumbled upon was that the answer to the fundamental question we were asked will depend on the way that you coarse grain the system. We don't know the right way to coarse grain the system, but certainly the answer you get will depend on how you do that. In a related result, we realized, of course, the information time dependence, whether or not it's constant or increasing or decreasing, depends a lot on how you define the system and what you mean by isolated. So if you consider the quantum isolated system we just talked about, then you have conservation of information. If you are allowed to use Shannon information to talk about the distribution of nuclei, which you may or may not allowed to be doing, but if you're allowed to do that, then it will go up and down. So the result will be sort of system dependent, and we don't have a fundamental a priori way to define that. Another interesting concept that came up during the discussion was one of free information. We kind of changed gears and started talking about this question that the group 4 talked about, this relation between information and entropy. And it's clear that if you have a completely random situation which maximizes Shannon information, then it's not very complex and it's not very interesting. So we came up with the concept of free information. Just like there's energy and there's free energy in thermodynamics, there's probably a concept that we haven't been able to define yet called free information, which is kind of the information that might be useful to do something. Also along that lines of complexity, for those systems in which you can use Shannon information, for those systems in which you do have a well-defined probability distribution, for those systems, then one prerequisite for interesting complexity is that the probability distribution is non-flat. Because if it's flat uniform, then you're maximizing information and then you don't have any interesting complexity. It was then floated that the power law distributions of probability in those kinds of systems might be the most interesting. And then we had a nice discussion about whether there's a preferred power law or not. Because if the power law goes flat and zero, then you're back to maximum information. If it goes really, really, really steep, then things are very, very highly clustered, and then each new piece of data doesn't give you very much more information. So there must be some intermediate in between, but we don't know how to do the rest of the problem. But I think power law probability distributions probably play an interesting role in this business. We also realized or talked about the fact that correlations matter, and that the correlations they matter just in terms of the mathematics of how you actually do the statistics, but they also matter in the sense that it's actually the laws of physics, the rules that govern the universe that determine those correlations, which ultimately give you those probability distributions. And finally, we talked about the fact that Shannon information theory is undefined in the continuum limit, and that maybe once you do something else, mutual information was one candidate, and the mutual information is interesting because it includes correlations, which are another important thing that we hit upon. And then, of course, the conclusion is that we have a lot of work to do.
Thanks. Okay, it's gone, but I believe the next one was fundamental limits on information content or processing. It looks like Adam is stepping up to the plate.
Yeah, so there were 4 people in my group: David Finkelstein, Seth Lloyd, Raphael Busso, and myself, Adam Brown. And we were answering the question, are there fundamental limits on the information processing and storage, which is 2 questions with 2 answers, both of which we decided were yes. So limits derive from limited resources, and the limited resources that we thought about were space-time. Specifically, in a finite region of space-time, there's only a finite information content that can be stored and a finite amount of information processing that can be done, which derive both from the finiteness of G and the finiteness of h bar, the finiteness of the gravitational constant and Planck's constant. It's a story that's familiar, I'm sure, to many people in the audience. It starts with the seemingly trite observation that if you try to cram too many hard drives into a given region of space-time, the hard drives undergo gravitational collapse and form a black hole. It's a prediction of our best theories, so but I'm sure you can work on that, Don. And it ends with the celebrated holographic bound made precise by Raphael Busso on the amount of information that can be stored in a given area, which is that the total amount of information in a given region is bounded by the area of that region in Planck units. There's another computational bound made precise by Seth Lloyd that says the number of computations that can be done, of operations, computational operations in a given region, is given by a similar bound. In fact, the area of that region in Planck units, roughly speaking. And then David Finkelstein warned that even these limits may be optimistic, that any limits assuming the space-time classical continuum are probably optimistic. That's what we did.
So there were 17 of us. Actually, remarkable. We achieved almost consensus, all but one, in 2 important points. So we started out with the most famous deduction in Western thought, namely René Descartes' "Je pense, donc je suis," which he later translated as cogito ergo sum. In other words, the one thing I'm utterly certain of is the fact that I'm conscious. Everything else is secondary. Everything else, including the knowledge that there are people out there in black holes, comes secondary. So with that in mind, we took a poll and we asked, is consciousness important? And everybody but one agreed that it was, which is good, because a lot of philosophers think it's not. So that's reassuring. So then we had a debate about, we talked actually about various facts relating to the current experimental approaches. So consciousness right now has been, over the last 20 years, a semi-popular topic in brain science and cognitive science, and people focus, and we talked about that, people focus on so-called the neuronal and the behavioral correlates. In other words, what type of behavior do we associate with consciousness, particularly in people, but also in animals? Or what type of neural activity is a particular type of, a specific type of neural activity that we associate with conscious activity? But then what we really want, and Giulio Tononi and Larissa articulated this, and we want an underlying theory. We don't want just correlates, but we want an underlying theory of consciousness that tells us whether the system in front of us is conscious and is not conscious. And then we had a very vigorous debate about things like can physicalism ultimately give a satisfactory account for consciousness? By the way, by consciousness, we mean sort of what we meant conscious experiences, raw experiences, the feels, the sounds and sights of life, pains and pleasures and reds and blues and high seas and all of that stuff. That's consciousness. Can physicalism ultimately account? In other words, can we take a physics, maybe enlarge it by some yet to be discovered laws? Can that account for consciousness, or do we need some additional soul stuff or some other spooky stuff? All but one person agreed that ultimately we can do that. We then had a long debate about, is consciousness fundamental or is it an emergent property? And there we didn't achieve resolution because we had different definitions of what do we mean by fundamental. Is charge a fundamental property? Or, is consciousness like charge? Is it a fundamental property? What do people mean by that? Or is it something emergent? What do people mean by that? We didn't really achieve a consensus. Some of us thought it is fundamental and has to be included in any future physics. Other people thought, no, it derives from its supervenient to physics. We also had a long debate that we didn't conclude about what in the field is known as the hard versus easy problem, or the easy versus hard problem. Hard spelled with a capital H, like in impossible hard. This is a distinction popularized by the philosopher David Chalmers, who argues it's essentially a reformulation of the classical mind-body problem, who argues that the easy problem is just relating, looking at the neuronal footprints of consciousness, or, what do people do when they're conscious and what can you do when you're not, when you're unconscious, all of that, that's the easy problem. The really hard problem is accounting ultimately for the phenomenological aspect, the felt aspect, the raw feelings in terms of physicalism. And some people believe that this is a very important distinction and will be critical, and it will not be possible to overcome that using sort of our understanding of science, while other people think this is a modern form of defeatism, i.e., we've heard very often over the last several centuries that physics is fine, but physics can never describe phenomena X, like physics can never describe life or can never describe what happens on other stars or things like that. And of course, historically, that has been shown to be false. And thereupon, I think we dissolved and we went swimming in workout.